Hello, hello. Today I'm going to be explaining what a neural network is. I'm doing this so that a future video I'm trying to make is going to be me making my own neural network and using it to classify certain things. And I was just making sure that if you had any questions regarding that topic, that you could refer to this video. So to get started, let's look at a perceptron. Let me get my little pencil tool. So Perceptron is pretty much a basic building block of neural networks, designed to mimic kind of like a single neuron in a human brain. Uh, each perceptron has inputs. Here we go, is little input layer kind of. Uh, and each input is multiplied by a weight. So like W1, W2. Each weight is kind of individual to the input it's with, or kind of tied to. Uh, and the weight kind of determines like how important each of these are. So let's say we were trying to classify if this was a dog, or yeah, but there you input a picture. Uh, this is going to be just a very high level, I guess, comparison I'm about to make. But basically, you input a picture, and all these inputs, it's trying to determine if the picture is a picture of a dog. And it's like, oh, does it have floppy ears? And how important is that? And so let's say kind of important, the weight would be like, 0.5. Uh, does it have a sharp teeth? Weight would be, 0.3, so on and so forth. And then it would move on and add these weighted inputs together and include a small additional value called a bias, which you can kind of represent with like instead of an input, just a 1 times a W0, or a, weight of, not of 0, but sorry, well, I guess the 0.5 looks like it's the bias there. But basically, that's what this summation sign is you add pretty much y equals mx plus b, if you remember your slope formula, uh, mx, except instead of mx, it's wx, and plus b is the bias. So you can kind of see that equation right here. If you notice, the w and the x are capitalized and the b is lowercase. This is because typically when writing these things out, if it is a vector, and a vector means something of multiple values, so like 0.6 and then 0.5 and then so on and so forth, uh, that would be a vector, and vectors are represented by capital letters. So since there are multiple inputs and multiple weights associated with each input, both of those would be vectors. But there is only one bias that gets added on at the end, so that is just a singular lowercase. And then after that, it gets thrown into an activation function, which is this g here. I just said g equals activation function. There are a couple common types, but as you can see, so sigmoid is a common type. Something it does is it takes whatever input you give it, and it will shove it between 0 and 1. Uh, and ReLU, or rectified linear unit, I believe is what it stands for. Um, if it is a negative value, it is 0, and if it is a positive value, it is whatever that value is, versus in sigmoid, the highest it can go is 1, versus this, I think, and it'll be whatever the input is if it's over 0. And this one, if it's negative, it doesn't really, I don't think, ever reach 0. It might, but this one is immediately 0 if it is not positive. Uh, so this is a perceptron. If you know what a neural network kind of looks like, you can kind of see some similarities. This is pretty much, I guess, like a linear regression. Uh, and so I think I can. Oh, okay, wait. So we're gonna save that for a little bit. Um, Actually, we might as well go down. So if you're looking kind of for, this is how I visualize a neural network and like the training process, like what that actually is. So think of it as a linear regression, which if you don't know what that is, uh, make a better one than that. So imagine there's a graph and you have a bunch of points. Uh, and these points, let's say, cluster around places, here, it'll cluster maybe here as well, and then maybe up here. Uh, Linear regression is trying to find the line of best fit. So if it's all here, it'd probably be something like that. Uh, because since it's a linear regression, it's a straight line. Though a neural network does pretty much multiple linear regressions so that it can find the line of best fit that, it'll be able to curve and move around. And, if we did one here, it'd probably be something more akin to that. Uh, and this is because whenever you feed a neural network an input, it pretty much, deconstructs and makes it uh, data. And so it can kind of, you can visualize it on a graph. For example, if you feed it an image of a cat or something like that, it would break down the pixels and it would see like, oh, like, this pixel here, this pixel here, this pixel here, give different weights. Each pixel would be an input. So, if it was a 64 by 64 image, it would have however much 60 times or 64 times 64 is, uh, an inputs, and the output would be, but if you're trying to classify if it's a dog or cat, it would just be, probably you'd get away with like one output where, let's say you're trying to classify it as a dog, and if it's not a dog, then it is a cat. Assuming that, I guess, the what you only receive dog or cat pictures. Um, you could get away with one output, and let's say it would be like 0.6, and that'd be like, oh, it's 60% chance that it's a dog or whatever we said before, which means that, conversely, 40% chance that it's a cat. Uh, and then yeah, so it would break down and it would check like the pixel values for each of these. Typically, I believe when you do image recognition, you grayscale the pixels, so you don't actually care about the colors. You just care about the brightness, I guess, of it. So if something's darker or something's lighter, if it's darker, you can kind of see it's like an edge. So let's say you're trying to classify numbers. If it was like really dark around pixels that kind of form the shape of a three, and you fed it like a bunch of pictures of threes where people messily draw threes a whole bunch of times like that, it'd be able to see like, okay, well, these are all kind of matching a similar pattern. Each of these would, let's say be these red dots here, where they're not the exact same, but they're kind of clustered in a similar fashion. And so when you're training, your line will originally go something like, let me get a different color. It'll go something like, oh, this is a three, and then this is a four, and then this is a five, and then it'll train a little bit more, and it'll be like, oh, this is a three, and oh, this is a four, and oh, this is a five, and oh, and then it'll get better and better and better, ideally. What you don't want to happen is overtraining, where it would pretty much go from point to point to point to point to point, and pretty much if your threes do not look exactly like each of these, uh, then it just completely, does not think it's a three. Versus undertraining or underfitting or overfitting versus underfitting. Underfitting would be where it would not recognize even some of these as threes, its own input, pretty much. So there's a sweet spot where it learns enough of the traits without saying that like one of the traits is it has to be sloppily drawn, or it has to have like a longer bottom side, of the three bottom curve, I guess, like that, then top curve, or maybe the top part has to lean over, similar to this one. Uh, but yeah, so that's how you can think of, I guess, a neural network. If you have trouble visualizing it, which I originally did when I was learning about them. Basically, the inputs would be each of these little points, and the output or the trained model is the weights and biases that are associated with the finished version, pretty much after it's done with its training process. And training is just, again, trying to fit this best to the data points you're given. There is such thing as too much training and too little training that leads to over and underfitting. Uh, but if you find that sweet spot where you adjust it just enough to where you get the expected output you want every time, then uh, you can save that as your trained model, where you save your weights and biases, and that way you can just use that. And your weights and biases, you can imagine it as pretty much this equation, I guess. Um, but instead of variables, you actually do have like defined values for the weights and defined values for the biases. And then you can slide in your picture of like, oh, here is this, image right here. Is this a three? And those pixels would go into the input, and then it would run through this equation, apply the activation function, and then output a value, and hopefully it would be decently high. We'll give it a 0.7. It's a kind of bad three, honestly, 0.6. Though I guess or okay, yeah. So moving on. So this is a perceptron, kind of the basics of that. Let's go down here. So this is a neural network. Um, this is pretty much, if you can kind of see similarity to a perceptron, uh, except so here is the input layer. Oops, sorry. Here's the hidden layer. Here's the output layer. The input layer is pretty much the same as here, where it's just all the inputs being shoved in. Each input might be shoved into each neuron, depending on how you structure your neural network. Uh, though, as you can see, it's a fully connected neural network, so each input is connected to each layer of the hidden layer, or each, I guess, neuron is connected to each neuron in the following layer. So same with the hidden layer to the output layer. Uh, that way, you pass in a input vector to each of the input neurons, and then they will each pass a vector to each of the. Well, they won't each pass a vector. Each will pass a output value, which would be like the output of this perceptron, a single value. But since each one is passing their outputs to each of these neurons, they will still be receiving the outputs of like this, neuron one, neuron two, neuron three, so forth. And then same here, going to the output layer. You may be curious, so let's walk through, I guess, an example for this. So let's say here you're trying to classify something that is a if an image is a dog. Well, let's just do numbers again, just because I can draw numbers better. Wow. As I draw that, if a image is a 1, a 2, or a 3. And so you pass in the pixels again, so there'd probably be more than this. So we'll do a little dot dot dot. Uh, but let's say this pixel has a brightness of 0.73. This pixel has a brightness of 0.1. This has one of 0. Now it's a blank. Or I guess, yeah, it's white. There's nothing filled in. And this is a zero point 0.9. It's very dark, like something that was like an edge of something that was drawn on. And if we zoom in really close, you can kind of not see. See, I lied. Uh, a lot of times the image sets in these, it'll have the numbers will be drawn, and it will, I guess, have, how do I describe it? Like, it's not just 1 1 1 1 1, and then everything else is 0. The edges around this will be it's almost like a small gradient, kind of like if you were to draw with like a graphite pen, I guess, or a pencil. um the actual drawing you're doing is pretty dark, and then around that there's like slightly less dark edges, and it's just let me see if I can actually pull up a picture. Here we go. Something like, here we go. So see how it's not all, well, let's just use this one. Yeah. Oh, wow. Is it a GIF? That's kind of actually annoying. But, so, zeros for it's not filled in, then you see 0.1 where there's like a tad bit, the 0.6, it's a little bit more, and then the ones where it's like directly was drawn upon. Let's yank that over here. Then we have, it would get fed into, so pretty much go through a mini perceptron where it does, like, so this whole part is kind of shoved into each neuron, where the output would be the output along this edge to each of these, which is why we went over the perceptron first, so you can kind of not be overwhelmed, hopefully. And the input would be the input here, or I guess here, depending on if you're taking in a single pixel value or every pixel value for each individual neuron. This takes place inside of this neuron, where it uses the weights and summations. Actually, that might occur along these edges. Then it produces an output, and then it aggregates all the outputs from all these and these nodes, and then the process begins again. And then let's say, again, we're looking at this right here as our image, uh, and these different outputs. This is like the probability that it is a 1. This is the probability that it's a 2. 2. The probability it's a 3. 1, it'd probably be very low. Give it a 0.2. See, we're just learning how bad I can draw with a mouse. For 2, it still has that curve at the top, but and then kind of like a little there, but it does not go this way. It goes this way. So it'll probably be something like let's go to 0.4. Oh, psych. 0.3. This will be 0.5. Just because I'm bad. You can do so. This would be, I guess, the probability that the whole image is a 3. There are also like multi-class, or I guess multi-classification neural networks. So if you're trying to see if a 3 is present in this image, then these don't necessarily have to add to 1. This could be like a 0.7. This could be a 0.5, and then that could still be a 0.2. Uh, just because it's like, oh yeah, it does share a lot of characteristics with the 2, but it falls short, in this area right here. So give it a kind of low percentage where it's like not really super convinced that there's a 2 in the image. Here it's pretty convinced that there's a 3 in the image, so it is rating that 70% chance that there's a 3. Um, so I guess it's individualistic. So you could pass in an image where it's like 3, 2, and then a small 1, and then each of these would hopefully be increased. So like this would be a 0.6, this would be a 0.7, this would be a 9 maybe. Or I mean, honestly, since there was a 3 already, that could be 0.7. This could be, since the 2 is kind of smaller, 0.6, and this would probably be 0.5. Just as the probability that there is that in this image. Uh, but yeah, so neural networks, they're not very scary. Um, let's quick recap. A model is a trained version of your network, contains the very specific weights and biases that define how it will predict your new data or classify new data. Predicting if you're predicting like stocks or something like that, and classify like what my examples have been. We've also been going over a feed-forward neural network, which has like a unidirectional flow. It all goes to the right. There is a different type of neural network called a RNN, or recurrent neural network, which has a looping structure, which can help show how previous outputs affect subsequent inputs. Something like that I might either go over in another video. If you're interested, you can look it up on your own. That is more used for text processing and text generation, I think, um, versus classification. And then neural networks, they're useful for complex problems where traditional algorithms may struggle, like image and speech recognition / classification. And then, it quote unquote learns. So as we learned, there's no brain in the side of the computer doing any real thinking. It's just math where you will take derivatives, and you will try to fit this line as best you can to your input data. Uh, Maybe not as best you can to avoid overfitting, but you try to get, I guess, a good enough line to where if you get a new data point that is in this area, let me make it a little bigger, that it probably would hopefully, honestly, I did put that in a spot where it could be a couple things, I guess. But let's say if there's a point right here, then it would be like, oh, that would be, let's say this is, a cluster of 3s. It'd be like, that's probably a 3. Um, so if you have any questions, any comments, any concerns, please leave them down below, and I can try to answer them as best I can. This was supposed to be kind of a rudimentary explanation. I will be going over the implementation of a neural network, hopefully in a future video. My implementation I'm going to be using would be, let me see if I can get some space. Pretty much, I built a program where it will, web scrape a bunch of wallpapers and, display them in my GUI I set up, and then give me a bunch of numbers at the bottom, 1, 2, 3 through 10, where I can rate them. Wow, that was bad numbers all around. And so, I go through this and pretty much save a bunch of trained data where it's like, here's a set of images that he thinks are, 10s, 9s, 8, 7, 6, 5, 4, blah, blah, blah. And then I'm trying to train the neural network on this data so that it can predict what wallpapers I would like, just because I do like to customize my laptop. I like to customize, I guess, how everything looks. And I don't really like the same thing too often. So currently I'm having to just shuffle through a playlist of like I think 10 wallpapers or maybe 12 or something every hour, and it's kind of nice. But I was like, what if I could just have it where every day it would take in maybe 10 new wallpapers, or maybe it would scrape a website until the model determined or found 10 wallpapers it thinks I would like. Uh, Pretty much, maybe I would get a new set of 100 images every day, or maybe I'll gather from different sources like Wikipedia's art of the day or something. And if the model is like, yeah, based on the images he's recommended, this is a point 0.8. Probably have like a boundary of like if it's less than a point 0.7, then we just don't take it. But if it's or less than a point 0.8, I guess, 80% Bs or higher, um, then it'll add it to my little wallpaper collection. And to, I guess, avoid storing too much stuff, I can have another scripter program that'll go through and delete all wallpapers that are older than a certain date. You could say just older than a week, and then every day it'll add new stuff. Um, and then I guess we'll also, to avoid it getting a series of bad wallpapers and not finding anything, have it where if it'll have like a minimum of 20 wallpapers in the folder, so that if it didn't find anything for the past couple days and it's deleting a bunch of the wallpapers, it won't delete all of them if we can't find anything good. So if that sounds interesting to you, I will hopefully be done creating it soon-ish. I won't make any promises. I do have exams, uh, but I will walk y'all through, and hopefully y'all can see some implementation of the topics we discussed today. So thank you very much.